And that's what we're going to be doing in lab on Tuesday also. So you may have gotten into it a little bit when you went through the pre-lab stuff. You may have seen some of the stuff we're going to be talking about today. So this is another lab where we'll be doing a little bit more in lab than what we do in class in terms of calculations and things. So if you want some help with those calculations, I'll have a web form so you can see how that goes. Well, we also need to share class data, so you actually need to put the data in the web form today. I forgot about that. All right. What are solutions? We've talked about them. I mean, we've used them. You've probably heard of them. What are they? Anybody have a good idea about that? No? Nothing? Just don't feel like talking today?
A combination of the solvent and solute?
Yep. So the parts of a solution we define as a solvent and a solute. We'll talk about that in a second. A solution itself is really just a type of another word for a homogeneous mixture. The only real difference is that when we talk about a solution, when we use that term solution, we're really talking about like at the molecular level. So the different parts of a mixture are really connected at the molecular level. So you don't have big clumps of different things existing in there at all. It's all completely broken up. And the different parts of a solution are usually called the solute and the solvent. And we generally say that a solute is dissolved in a solvent. So if we imagine like taking water and dissolving salt in it, sodium chloride, we would say the sodium chloride is the solute and the water is the solvent. But we want to, again, define these a little bit more generally because there are lots of different types of solutions besides just a solid dissolving in a liquid. So the only real definitions we can say for solute and solvent is a solute is the thing there's less of, and a solvent is the thing that there's more of. And there's one kind of big exception to that. And that is that water is almost always the solvent, even when there's less of it than the other stuff. So if you imagine something like looking at percentages of alcohol on beverages, something like wine would have a percentage of 12 or 13% alcohol. So that's clearly a solution of alcohol in water. But then if you have some like really high proof liquor, like I have in my bag here, I don't have high proof liquor in my bag. Does anybody? No? Okay, good. Don't bring it to school. But if you had really high proof liquor that was like 80% or 60% alcohol, that's really actually more alcohol than water because it's more than 50%. So it's really more like a solution of water in alcohol. But since it's water there, we still call water the solvent, and we still base our percentage off of that. The book has some good examples of some different types of solutions that maybe we don't always think about. So I'll put that in here as well. When we think of a solution, we usually think of that middle section, the liquid solutions, dissolving something in water. So you could imagine like seawater, salt dissolved in water. You can even think about liquid in water, like alcohol in water or vinegar in water, gas in water, like soda, carbon dioxide dissolved in water. Those are still all kind of typical solutions that we think of, but solutions don't have to be in the liquid phase. So you can have a gas solution, gas dissolved in a gas, like air. What would be, well, it says it there, the primary solvent would be nitrogen just because there's more nitrogen in air, and we can imagine the other gases as being dissolved in the air. Same thing in a solid. You can have something like steel, which is mostly iron, but then there's other stuff dissolved in that steel, like carbon or chromium or nickel or whatever else, or dissolved in that iron that makes the steel. And depending on the ratios of those other ingredients, that's going to change the properties and change what the what that material does. Brass is another example they give here. It's mostly copper, but it has zinc dissolved in it as well. And because of this idea of the mixture like at the atomic or molecular scale, if you were to zoom way, way, way in with a microscope on steel or brass, you would mostly see that those chemicals were pretty evenly distributed throughout the substance. And you wouldn't really see like specific pieces of different things, although depending on the material, sometimes you do. So that's the basic idea of a solution. Let's kind of draw what that looks like and what it is involved when we're actually making a solution. Title this. Dissolving sodium chloride in water. So we start with our sodium chloride. Sodium chloride in the solid phase, or solid state. And that just looks like a bunch of little balls all packed together, sodium ions and chloride ions that are kind of packed together as tightly as possible. We'll draw our sodium as blue and our chloride as red. Chloride ions are bigger than sodium ions. Sorry, this is really annoying if you're using separate pens. But anyway, something like that. Kind of all packed in together in different ways, and that's our sodium chloride. And what are the forces that hold those things together?
The ionic bond?
Yeah, ionic bonds. Held together by ionic bonds. Those are really, really strong forces because melting points of salts like sodium chloride are really, really high. So very strong forces hold these things together. And yet, when they put in water, when sodium chloride is put in water, it breaks apart right away. So something interesting is going on here. It takes thousands of degrees to melt this thing, but if you just put it in water, it breaks apart right away. So what's going on? Well, to figure that out, we also need to look at the structure of the water. So what does liquid water look like at a molecular scale? Yeah. Right. So like you've got your water molecule, and then what's happening in between water molecules? Right, the polar interactions, the hydrogen bonding that we talked about. This is another chapter where we're going to go back to thinking about the intermolecular forces from the last chapter a lot. So let's review those. We've got hydrogen bonding in water. That's the strongest one. What are the other intermolecular forces that we talked about? No, covalent is inside the molecule. That's a type of a bond. What are the forces that hold different molecules together? So hydrogen bonding is one of them. That's what happens in water. And there's two other ones. Nobody? Make sure you go back and review this before the exam. But there are just dipole-dipole interactions or dipole-dipole forces for the polar molecules to hold each other together. And then does anybody remember the nonpolar one is called? How do nonpolar molecules hold each other together? Dispersion forces, yeah, thanks. So we're going to be talking about that today also. Okay, let's look at some water. So here's a water molecule, but then because it's liquid water, those water molecules are holding each other together as well. Okay. So those little dotted lines that hold water molecules together are called hydrogen bonds. Remember, we said that's kind of a confusing term because it sounds like a bond, like a covalent bond, but really it's just an attraction holding them together because of positive and negative polar things, like these kinds of things. We can draw those all over. So water is polar, it has a negative and a positive side, and that's what allows it to do these kinds of things. All right, so that's our sodium chloride and that's our water. When these things get together to form a solution, what happens is that the charged framework of the sodium chloride can kind of be infiltrated by the water molecules because they also have some polarity to them, because they also have some positive and negative. So they can start surrounding the ions. I'm going to kind of run out of space here, so I can draw it down here. When water and sodium chloride solid come together, what they can make is this matrix where we're going to draw them individually. Here's a sodium ion. And all around that sodium ion, that positively charged sodium ion with its strong positive charge, water molecules are going to orient themselves so that the negative part of the water is facing and kind of holding on to that sodium ion. The negative part of water is the O part. And because of that negative part over there, there can be some interactions with the sodium. Now, I drew it as a circle kind of on paper, but actually the water molecules would surround it on all sides in a sphere. So you make this whole sphere of water molecules around that sodium. And those interactions are kind of a combination of the intermolecular forces we talked about and the ionic forces involved because of the sodium. They're called ion dipole forces. So the ion is reacting with the dipole, or interacting with the dipole. And then on the other side of that, there's a lot more water than salt in a saltwater solution. So these water molecules are still attached to other water molecules, just as in the liquid. Right, we can kind of draw a whole thing going on with that. And then the chloride ion, which is negative, would be surrounded by other water molecules oriented with the positive side toward the chlorine, which is the hydrogen side. So they kind of have these sorts of interactions. And again, that would be in a whole sphere. And that's what we call, that's kind of a molecular view of what we call an aqueous solution of sodium chloride. So the ionic matrix is actually broken apart, and water molecules surround those ions. And that's how it's able to overcome that energy difference. And in fact, when you dissolve sodium chloride in water, if you measure the heat really carefully, it actually gives off a little bit of heat, which means that the ions surrounded by water like that are more stable, right? The bottom of the energy curve are lower in energy than the initial ones, even though it takes thousands of degrees to break up that sodium chloride if we're just trying to melt it. There's a couple of reasons for that. One is just the number of interactions. So each ion is going to have a whole bunch of these water molecules that can go around it. Even though each interaction is smaller, the sum of all of them ends up being something pretty substantial. And then there's something else called entropy, which is kind of the disorder in how this stuff is arranged that makes it more favorable for that to happen. So that's why we get this type of an interaction, this type of a product when you have a solution. So you've got a polar solute, the sodium chloride, you've got a polar solvent, the water, and we get these kinds of interactions. So let's look at what happens when we don't have that, when we have a kind of a mismatch in polarity. Let's take our water again. Let's look at water and oil. Does anybody know what happens when you mix water and oil? They split. They don't dissolve, right? Does anybody know which one goes on top?
The oil.
The oil goes on top, yeah. Oil is less dense than water, so it goes on top. If you see you look at like puddles outside that have some gas or oil on the top and they kind of have that rainbowy look to them, it's because of that thin layer on top. Yeah. So water and oil. Let's look at what's happening at the molecular level and see if we can explain why they don't mix by looking at their structures. So we'll draw that water matrix again, where the water molecules are all interacting in these polar ways. The actual structure of this, we're kind of just drawing it loosely, but if you, because it's a liquid and it is disordered, but if you freeze water, it actually makes this really nice hexagonal kind of honeycomb looking network throughout. But there's water, right? And then what does oil look like? We know what oils look like? I don't know if I'm going to talk about that. There are these long chains of carbon and hydrogen. So long chains of carbon and hydrogen that are connected in the middle in kind of a triple thing. And they just keep going. So when I say lots of carbons, I mean like 20 or so per chain, between 12 and 25. So that's oil. And the way that those kind of stack up is like this. So there's those three chains. Let's actually make them even bigger. And what kind of intermolecular forces are those going to interact with? Is that going to be polar or non-polar? You want to take a guess? Polar or non-polar? Oil? No guesses? I mean, you got a 50-50 shot. Non-polar, yes, very good. It's non-polar. Make sure you go back and read that stuff because that will be coming up in this chapter also before the exam. But yeah, carbon and hydrogen do not have a strong difference in electronegativity. So carbon, hydrogen-based stuff, hydrocarbons, gasolines, oils, all that kind of stuff is non-polar. So if it's non-polar, how does it attract? How do the molecules attract each other? What was that? What were those forces called? Dispersion forces, yeah. So these things will line up kind of like this. If we imagine these kind of long chains. And those are going to be connected by these dispersion forces. So these kind of weak forces that hold together based on these induced dipoles. Now we talked about dispersion forces being weaker, and that's certainly true. But when molecules get big enough, then the overall force is actually pretty strong. And that's why oil is a viscous, non-volatile liquid. Like it's pretty happy to just stay a liquid because the molecules are so big that there's enough dispersion force to actually hold everything together pretty well. So if water is a tiny molecule, so the fact that it's also a liquid speaks to how strong that hydrogen bonding is. But large molecules we kind of expect to stick together pretty well, and that's what happens in oils. So those things stick together pretty well. The oils stick together pretty well. And so we don't see any interaction. Say no solution. And the reason there's no solution is because it costs energy to break up those water molecules from each other. We talked about that when we talked about boiling water, heat of vaporization. It takes energy to break those things apart. It also takes energy to break the oil molecules apart. And in the previous solution, same thing. It takes energy to break up the sodium and chloride, and it takes energy to break up the waters. But then you get all that energy back when you reorganize them in these kind of spheres. For the oil and water, that doesn't happen. Because when if you tried to reorganize them, they wouldn't be able to interact with each other. Because oil can't hydrogen bond and water doesn't have strong dispersion forces. So if water and oil kind of went together, all they would do is disrupt all those intermolecular forces without creating any new, like, better forces to make it even stronger. And so that means that just won't happen. They won't mix. So if you take oil and water, you mix it up, you can mechanically mix it up. You can like shake it really a lot or something, and you can mechanically break it up. But then over time, it'll reorganize itself into those layers again. And we'll see that in lab today also. So that's why polar and nonpolar materials won't make solutions together. Now the exceptions to this are molecules that can do both. How should I tell this? We'll say, get you a molecule that can do both. All right, get you molecules that can do both. So these will be ones with two different pieces of it. That's a reference to a song there. Sorry. So one example, like in a small way, would be something like this. This is ethanol. Ethanol is like the alcohol in alcohol. So on one side we have OH, which we know is good for hydrogen bonding and polar stuff. So that's going to interact with hydrogen bonding. But the other side of the molecule is going to have those dispersion nonpolar type forces because of the carbon and hydrogen. Now, ethanol is a pretty small molecule, so the difference in those two sides is not that big of a deal. And ethanol mostly just acts as a polar molecule. But ethanol is going to mix with things like fats and oils that water can't mix with. Just because it has like just enough non-polarity, has just enough of that carbon part to get in and make some dispersion forces. So that can kind of do both. And that works as then a better solvent. Another example is acetone, which we'll use in lab today. And we use that sometimes to clean out our glassware because it dissolves both things so well. Acetone is also a nail polish remover. If you've ever used that stuff, it has kind of a pretty distinctive smell. And one of the reasons that works well is not only is it a good solvent for the non-polar materials in nail polish, those are mostly non-polar materials, but also the polar materials in there that help it to bind to the nail, because nails are actually polar. So it can kind of do both of those things, and then it's also you can also mix it with water so that it can be disposed of. Other exceptions to this are, like extreme exceptions, are soaps. We know what a soap molecule looks like. Do we know what you make soap out of? Or, I mean, now we make them mostly out of like chemicals and stuff, but like, has anybody ever made soap from a natural product?
Soap in elementary school, but I can't, it was too long ago, I can't
remember. You remember?
Isn't it like fats?
Yeah, it's made out of fat. Yeah, you can take oils or fats and do a process called saponification, which is a chemical reaction, which literally means make into soap, that breaks it apart and turns it into a soap molecule. So a soap molecule is a fatty acid, which is this really long chain of carbon and hydrogen. I'm just going to draw it like a squiggly. And then at the end, it's got a carbon double bound with oxygens, and one of the oxygens actually has a negative charge on it. So this one's pretty extreme because it's got a huge section over here of just carbon and hydrogen that is completely nonpolar. And then over here, it's so polar, it's actually ionic. It's actually an ion, like it's charged. And that all exists in the same molecule. So when you put soap in water, what happens is that it orients itself so that the polar part faces the water and the nonpolar part gets away from the water. So in water, it makes this thing called a micelle that looks like this. The O's are on the outside, and then the long carbon-hydrogen chain kind of goes on the inside like this. And that happens also in 3 dimensions, so it's like a sphere. And these outer parts, remember, are all actually negatively charged. So the water molecules can line up with them, with their hydrogens, just like they would with any other negatively charged ion. There's can be some other stuff going on too. And so that allows this whole thing to get into water. But then the inside of that thing is completely nonpolar. So greases and oils get stuck in the middle, and then they can be dissolved in water. And that's why soaps can clean us, because the stuff we need to clean is mostly greases and oils, which are nonpolar, and we need to get them off with water, which is polar. So we put the grease in the, or we put the soaps in, we agitate it by rubbing your hands for 2 alphabet songs. Is that right?
15 to 20 seconds.
Yeah, I think 2 alphabet songs is what we tell the kids. Because you can sing the alphabet in that song. You guys know that song? Okay. And she'll look at me like, what the hell is the alphabet song? But yeah. So yeah, 15 to 20 seconds, you're agitating it, and the agitation is getting that grease and oil stuck inside those micelles, and then allowing those to organize and dissolve in the water. And so that's how soaps work. So we have this saying that is in the book that says like dissolves like. Have you heard this before? Like polar things dissolve polar things, nonpolar things dissolve nonpolar things. And we'll check that in lab today too with some examples. But I want you to think about it in a little bit more complicated terms than that. It's like dissolves like with respect to intermolecular forces, not just polarity. Because we would say that soaps are polar, but they really have a big nonpolar part. So that's not like breaking the rules. It's not really an exception. It's just saying these parts interact with these things, these parts interact with these things. And so if you think of it in terms of forces, that works in all situations. If you think about it as just like polar with polar, nonpolar with nonpolar, that doesn't always work. That's going to give us some trouble. All right, some words that you should know in relation to this stuff. Hydrophilic, what does that mean? Yeah, it means that root phil is like love, like, and hydro is water. So this is something that likes water, and this is what mostly we would just say is polar. Hydrophilic is more commonly used in like biological sciences and dealing with materials. If you talk about materials that can absorb water, that kind of thing, those are known as hydrophilic. And then what's the opposite of that?
Hydrophobic.
Yeah. And there's another name for this that's more often used in biology. Anybody know what that is? It starts with an L. For kind of the opposite, like describing nonpolar things. It's lipophilic. So those terms are used to mean nonpolar. In biology, we use hydrophilic and lipophilic. Lipo means like fats, so that's the nonpolar part of your body. But it's also important because cell membranes are nonpolar. There's a lipid membrane that acts as a barrier in cells, so that things that are polar, like ions, polar molecules, all the stuff going through our bloodstream, can't get into the cells that way. And then these molecules that can do both are called amphiphilic. So they have a polar part and a nonpolar part. And this idea of polarity and solubility is really important in biological systems. I mean, it's important everywhere, but especially in health-related things, because what is our body mostly? Water, right? So a lot of focus on, like, well, let's talk about drugs, like pharmaceutical things. If you're designing a new medication, you want it to be polar because it's got to dissolve in your blood to get through your body somewhere, you know, with the exception of certain types of things. But if you're taking a pill or if you're getting an intravenous injection or something, that needs to be polar so that the blood can carry it around. But also, it needs to be able to get into cells. And if it's too polar, it's not going to get into the cells properly. So the molecule has to be designed with areas of polarity so that it can be dissolved, but then also it can be non-polar enough to actually get into the cells through the lipid membranes. So there are various tricks that drug designers use for that, making salts of things that then get changed once they're in your body. But a lot of pharmaceutical production and drug design goes into thinking about these kinds of issues. This is a major part of that. It's called bioavailability. It's basically the idea that you could make a molecule that perfectly fits your thing that you're trying to hurt or help or whatever, but if you can't actually get it into that spot in the cell and get it into the body in that way, it's not really going to be a useful drug. So a lot of this stuff is thought of in those contexts. Okay. Next thing we're going to talk about is directly applicable to lab today. There we go. Solubility. I'm going to pull this picture out of here. There we go. So what we're going to do in lab today is experimentally construct a diagram like this. There it is. This is called a solubility curve or a solubility chart. Solubility is defined as how much solute can dissolve in 100 grams of solvent, which is usually water. That's what we're going to work with today. So how much can you actually put in there before it just stops dissolving and falls to the bottom of your container? If you have the maximum amount of solute in a solvent, anybody know what that's called? A solution that has the maximum amount of solute in it? Saturation. Yeah, it's called saturated. Now, if you have a saturated solution, that means that if you put in any more solute, it'll simply fall to the bottom of the container and it won't dissolve in the water. If you're unsaturated, meaning less than that, then you can still put some more in and have it actually dissolve and break up in solution. So this chart is basically saying how much makes it saturated at different temperatures. So let's look at room temperature, a little over 20 degrees, and let's take sodium chloride. So this chart tells us that at about 20 some degrees at room temperature, a little less than 40 grams of sodium chloride should dissolve in 100 grams of water. So you got 100 grams of water, you should be able to put a little less than 40 grams in before it stops dissolving. Now that might take some time. So you might, like when you dump the salt in right away, you might not see it all dissolve. But if you stir it and you wait a while, eventually it should all dissolve at that temperature. Okay. Then if you heat it up close to boiling, you should be able to get another gram or two in there. So sodium chloride doesn't have a big change in temperature. But let's take something like glucose, which is a kind of sugar. So first of all, glucose is way more soluble than sodium chloride because you can get more of it in at the same temperature. So you get about 80 grams at room temperature in 100 grams of water. And then as you increase the temperature, look at what happens here. The solubility increases much more. Looks more like an exponential type curve instead of linear. And so that shows us that even raising the temperature a little bit can increase the solubility substantially. And if you look at those numbers, it's actually kind of crazy. Up there, once you get above 30 degrees or so, it's almost more like your solution is water dissolving in glucose because you now have more than 100 grams of glucose. You've got more glucose than water in that solution. So you can see some things are more soluble than others, and they are more or less soluble. The general trend, and this chart only shows this type, but the general trend is that things get more soluble as you increase the temperature. There are some solutions where that's not the case, where the line actually goes the other way, and it becomes less soluble at higher temperatures. But mostly we're going to see this. So the one we're going to work with in lab today is potassium nitrate, this orange line. And what we're going to do is split up in the class, and everybody's going to test a different amount of potassium nitrate. So one way that you can check this, the hard way I would say, is hold some water at a specific temperature and then carefully add an amount of whatever, we'll say potassium nitrate, until it stops dissolving, and then figure out how much you had to add to get it to stop dissolving. That's a really difficult thing to do because one, it's hard to keep something at one precise absolute temperature, and two, as you add the potassium nitrate, it's not only going to change the temperature, but you have to know exactly when it's going to stop dissolving, and that's kind of hard to see as well. So that's not really a great way to do it. How we do it instead is we put a certain amount of solute in water so that it doesn't really dissolve, and then we heat it up until it does all dissolve, and then we let it cool, and we watch for that moment at which some of it starts coming out. So it's, and so like you'll see, and that's what you'll do in lab today. You'll see the potassium nitrate coming out of solution, like all of a sudden it'll get cloudy. And that's the point at which it's no longer saturated. So then you measure that temperature, and that tells us exactly where on that curve that amount goes. And once we put all the class together, all the class data together, we should get a nice curve kind of like this one for potassium nitrate. All right, so that's how you measure solubility. The other exception to this is gases. Gases have the opposite behavior. And what I mean by that is, let's say you have a gas dissolved in water, like you have a carbonated beverage. What's your favorite carbonated beverage? Anybody have a favorite? Nobody really likes it?
Soda water.
Soda water? Just plain carbonated water? All right. So let's say you have a can of soda water or a bottle, and you leave it open. Is it going to go flatter faster in the fridge or on the counter? Anybody know? What about if you leave it outside in the summer? Does it go flat faster or slower?
Faster.
Faster. Yeah, that's right. And so that's showing the opposite thing here, that when a gas is dissolved in water, the higher temperature makes it less soluble, and the lower temperature makes it more soluble. So a gas is more soluble at a lower temperature. Not good so far? Everybody's okay with this? Okay. So that's part of the lab today, is measuring the solubility. Another part of lab today, well, the other one is going to be measuring polar versus nonpolar things, whether they mix together or not. And then there's also a part where we're going to look at concentration. Concentration is how we measure solutions. If you think about, like, say you have a sodium chloride solution and you want a certain amount of sodium chloride for a reaction or something, you have to have a way of knowing how much sodium chloride you're getting out of that solution. And you can't weigh it because most of the solution is water. You can't measure it by volume because, again, it's mostly water. You can't like measure its pressure or something because it's a liquid. So how do we figure out how much solute is in a given amount of solvent? That's what we need a concentration for. So the concentration is the amount of solute in a given amount of solution. So that gives us kind of a fraction like this. And this is a good way to remember how to calculate concentration. With a couple exceptions that we're not going to look at in this class, concentration can be thought of as solute divided by solution. So amount of solute divided by the amount of solution. Now, amount can be measured in different ways, so we're going to look at a couple different ways that it's measured. But of all the different ways you can measure concentration, they fit into this simple fraction. So you have some amount of solute divided by some amount of solution. And that gives you your concentration. We're going to look specifically at two types of concentrations here. First one is called mass percent, or percent by mass. It's written percent M over M. There's three types of percentages that are used in solutions. We're going to focus on this one, but the other ones are percent V over V, which is percent by volume. That's like how much alcohol is in something would be measured. And there's also mass by volume, which is how much mass in a certain amount of volume. It's a different calculation. So you've got mass, percent by volume, and percent mass by volume. We're not going to really look at those second two, but it is important to know what you're looking at when you look up concentration. So if you look at like an IV bag or some other kind of a solution that has something in it, and it's giving the concentrations, if it gives percent, it will usually give some sort of a symbol like M over M to tell you what type of a percent it is, because the numbers are going to be different whether you're measuring in grams or milliliters or whatever. So mass percent is the first one. This is a simple one because it is just a percentage. So you're going to measure the grams of solute divided by grams of solution times 100%. And I say grams, but really you can use any mass. Could be pounds, could be ounces, could be whatever. Because it's a percentage, that should always be the same, as long as you're using the same unit on the top and on the bottom. So grams solute over grams of solution, or ounces solute over ounces of solution, or whatever you like is fine. The important thing to note here is that the denominator, the bottom part, is solution and not solvent. So if you take 10 grams of salt and 50 grams of water, you don't find the percent by dividing 10 by 50. You divide 10 by 60 because you've got to look at the whole mass of the solution. The nice thing about this type of solution, or of concentration measurement, is it's really easy to make a solution. So if I tell you that I want, let's try this. I want a 10% by mass sodium chloride solution. Okay. How much would you put in? Well, I would never ask you to make me solutions. I can make my own solutions. But let's say you want a 10% mass by mass, percent by mass solution. How much stuff would you need to mix to put that together? So you don't need to do any fancy calculations with moles or whatever, anything like that. You just need to say, okay, let's say we want 100 milliliters of solution or 100 grams of solution. So we put that in the denominator. And if we want a 10% solution, that just means we need 10 grams of sodium chloride. And that's a 10% solution. So that's pretty simple. You put a beaker on the thing, on the balance. You add your 10 grams of sodium chloride, and then you add water until it comes up to 100 grams. And you got it. You mix it together, you've got your solution of a particular percent. So this is used in when you don't care about the really like the very specific, precise molecular amounts of these things. Like you're not using it in a reaction, you're just using it for washing something or for doing some kind of a test or something where you don't need to know exactly, like you don't need to know the moles basically. But in chemistry, we often do need to know the moles because we're using something in an experiment. So when we're going to use something in a chemical reaction, we want to know usually how many moles are in there. So we use a different measure that works a little bit better called molarity. The molarity symbol is just a big capital M. I usually put a little like curl or something on the bottom just to differentiate it from other types of big M's. But you'll see in the book, it's mostly just, it's like a big M. So molarity is moles of solute per liters of solution. Okay, so moles divided by liters. So if you're preparing a solution in molarity, it takes an extra step because you have to calculate how many grams you need. So you have to do a mole to gram conversion. But if you're using it in a reaction, it saves you a step because you don't have to convert grams to moles. You can just figure it out based on this. So let me show you how that works. Let's say we want 1.3 moles of sodium chloride. Or how much of a 2 molar solution, molar is the name for like molarity, how much of a 2 molar solution do we need? We can use that molarity just like a conversion factor. So we can say that a 2 molar solution means that there are 2 moles of NaCl per every 1 liter of solution. So molar is moles per liter. So 2 molar is going to be 2 moles per 1 liter. So we would calculate that by starting with the 1.3 moles of NaCl and multiply it by a factor that gets us from moles of NaCl to liters of solution. And the factor that does just that is the molarity. So a 2 molar solution tells us that there are 2 moles in each liter. So that tells us we need 0.65 liters of solution, or 650 milliliters. If you're doing a reaction, it's easier to calculate how much you need in moles than in grams because you've got a smaller calculation that way. And then you can just do this and say, okay, I need 650 milliliters of the solution, and I've got the right number of moles for what I need. we're trying to make the solution, it does take an extra step. So we might say, and this is what we'll do in lab today, because in the lab we have to measure in grams. So we may need to do some conversions. So let's see if we can answer this one. What is the molarity oops, forgot a amount here. What is the molarity of a 500 milliliter solution with 15 grams of sodium chloride? So you make a solution, you just put in 15 grams of sodium chloride and fill that up to 500 milliliters of solution. What's that molarity? In order to get molarity, we need to divide moles by liters. We've got liters, well, we've got 500 milliliters, which is 0.5 liters, but we don't have moles. So we need to convert that 15 grams into moles first, and then we can divide by the volume. So 15 grams NaCl. We need to get rid of grams of NaCl and instead have moles of NaCl. So we add that together. Na is 23, Cl is 35.5. So that's 58.5. Oh, I don't have my calculator up yet. 15 divided by 58.5 is 0.26. Okay, so that tells us the moles of sodium chloride. And then we can get our concentration by putting that number of moles over the volume. Remember that the bottom of that fraction has to be in liters, not milliliters. So you have to convert to liters. So 0.26 divided by 0.5 is going to be 0.52. And so we would say that is a 0.52 molar sodium chloride solution. So make sure you practice that, these kinds of calculations. It doesn't really get more different from that, but look at those. The last thing that we want to look at, because of the biological implications, is sometimes we don't want the molarity of the whole substance. We want the molarity of the individual ions. So like if you were giving somebody some sort of a ionic substance in their blood, you might want to know how many total ions are you giving, or how much sodium are you giving, or how much chloride are you giving. So sometimes that molarity has to be adjusted. Let's say we had a 0.100 molar solution of sodium phosphate. Now sodium phosphate is Na3PO4. In that solution, we could describe that solution in a couple different ways. We could describe it as 0.1 molar Na3PO4. Okay, that's how we would make it, because the Na3PO4 would be the solid that we dissolve in the water. But we could also describe it in terms of each ion. There's only one phosphate ion per formula unit of sodium phosphate, right? So that means it's also 0.1 molar in phosphate. But it's triple that concentration in sodium. So to do that, we have to take the total and realize that there are 3 moles of sodium ions, because that little subscript 3, for every 1 mole of Na3PO4. So that ends up multiplying it by 3. And then we could also say that it is 0.4 molar in total ions. Now, because we know that when you dissolve something in water, the ions completely break up. So for every 1 Na3PO4 you dissolve in water, you get 4 particles coming out, 3 NAs and a PO4. So that's important. We're not going to get to it today, but on Thursday, we're going to talk about osmosis and osmotic pressure and the effects on blood cells and things like that. And it's important to have to note the total ionic concentration in those cases, because that's going to control that type of behavior. And so with molarity, that's very easy to do. With mass percent, that's a lot harder, because you have to think about like the mass of the ions, and also that's not really helpful for the medical part of that. So a lot of times when you look at an IV bag, the different types of solutes will be labeled in molarity because of how that interacts with the ionic load in our bodies, specifically in the intracellular fluid. So questions about that? We'll get into that next time. Okay, that's all I got for now. Do you want to do lab? You want to talk about lab right now, or wait till we get upstairs? What? Just do it now? As long as everybody's sitting? Okay. There's not that much to say.